So what I want to start by doing is doing some partial sums. So let's consider the summation for the harmonic series, okay? We know this diverges to infinity. We know that. But what I want to do is demonstrate something very simple but very, very important about how it diverges. So I'm going to start by doing some partial sums. So this is called S100. It's the 100th partial sum, okay? Now it's 1 plus a half plus a third, blah, 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 blah. Okay, so now if you look at the screen, can you all see the screen? Let me see if I can make this a little bit bigger. There we go, okay. Don't look at the fraction, look at the number. So I add up the first 100 terms, it's a little bit more than 5. Okay. So let's change that now to 1,000. And let's see what happened. First 100 terms was about 5. The first 1,000 terms, it's a little more than 7. Okay. That's interesting. So why are you showing us this, Mr. Brown? Well, let's go. How about the first million terms? This is the beauty of technology, that this can actually calculate this really fast. It's no longer giving us a quotient. The first million terms is a little more than 14. We know this diverges to infinity, and by the way, it's really easy now that you know the integral test, right? We did it by being clever. Remember, we grouped it in 2 to a power, so 2 and then 4, then 8, then 16. We grouped it that way to demonstrate. That was a very, very clever proof. But that wasn't the simplest proof. Doing the integral test would be the simplest proof. So what does the integral test say again? Do you remember? In general, let's do this so we don't forget. This is bounded by, do you remember? This is always going to be we'll call it f of x, where f of x is the same as a n. We just like x's from 1. Right? We could say f of n. And what was on this side? Do you remember?
Less than the integral from 2 to infinity.
No, not 2 to infinity.
Plus a1.
Plus a1.
Oh.
Remember, it's bounded by the integral and the integral plus the first term. That's why the integral is never equal to the sum. That's absolutely impossible, because a1 cannot be 0. But if it doesn't matter how big a1 is, that's a narrow bound. That's why if this is infinite, then this is infinite. If this is finite, then this is finite. It doesn't tell me what it adds up to. I just know it's finite. So then how do I figure out what it adds up to? Well, I can do things like this. Now here's the thing. How in the world do we get infinity as a conclusion? Here's the reason. Every time I raise the upper limit, our sum is raising, isn't it? Where's it changing though? It's changing in the integer part, not in the decimal part. Okay, you guys catching that first of all? It's the integer that's changing. So now let me go and change the problem a little bit just to demonstrate the power of that. Now let's do 1 over n squared. Okay? Now I'm going to do the first 100 terms. And it says, where is it? The answer is roughly 1.6 something. Okay, big deal. Okay, now let's do the first 1,000 terms. Okay, that answer was 1.6 something. I'm not going to write it down. What do you notice about this answer? It's also 1.6 something. In fact, it's almost the same answer, isn't it? Yeah, it is not the same answer, but the difference happened a few decimal places down the road. Now, let's go the first million terms here. And what do you notice? It looks like it's the same answer again, except now the changes occurred basically beyond the 10th decimal place. The changes didn't occur until about the 13th or 14th decimal place. Does everybody understand what I'm saying? So this is a convergent series. We know the sum of 1 over n squared converges, but what's the difference between that and something like the harmonic, which diverges? The harmonic is getting bigger, but it's not getting that much bigger, but it's getting bigger in the integers. Every time I raise the upper limit, the integer part is bigger than it was before. Here I did 1 over n squared. Every time we raised the upper limit, the changes occurred further and further and further out in the decimal places. That is the number one difference between a divergent and a convergent series. All convergent series as you raise the upper limit, the changes occur further and further out. That's why you can use technology to give a reasonable estimation. Well, what do I mean by estimation? Estimation isn't accurate. Yes, but if I could guarantee you as many decimals as you want, I just can't give you the exact value of the answer. But if I could guarantee you, for example, if I needed to know what the sum of the first million terms is, that's not going to be much different than infinite sum. Why? 1 over n squared. A million squared in my denominator. Right? That's 10 to the negative 12th power. That means I got to go out at least 12 digits before a decimal value is affected. That's what I'm saying. If I wanted 10 decimal place accuracy, I've absolutely guaranteed it if I do this. Okay? So, convergent, divergent. Now let's go back over. I'm going to change something slightly. Back to here. Okay, now I'm going to change something. We're going to introduce something today for the first time. We're going to introduce something called an alternating series. An alternating series is a series that changes sign on every term. It's okay to have negative terms in a series. It's not a big deal. But usually when we have negative terms in a series, we're thinking the entire series. Every term is negative. But what if every term alternated in sign? It would have a kind of a canceling effect in a sense, wouldn't it? If you think about it. So the one I'm going to use today is something of this form. And the reason I'm going to start with an exponent of n minus 1 rather than an exponent of n is I want the first term to be positive. It just makes it easier to talk about. So when I put n equal 1 in there, that's negative 1 to the 0th power, which is 1. And then the next term, okay, so this means this is a1 minus a2 plus a3 minus a4. This goes on forever and ever and ever and ever. Okay, so what's the big deal? Let's start with the harmonic series. Okay, let's start with the harmonic series. So I just now did negative 1 to the n minus 1 over n for n equal, I started with 1 to 100. But what that is that's going to be 1 minus a half plus a third minus a fourth, on and on and on, finishing at what? At minus 1 over 100. Is that right? Yeah. It'd be minus because that'd be 99 power. So I want to add up these guys. Roughly 0.688 something. Okay. So why is that a big deal? All right, let's do the first 1,000 terms now. And it adds up to obviously something way different. 69 something. Oh, okay. Let's go, I don't know, how about the first million terms? That seems to be my pattern here. I'm going to go the first million terms. And what do we got? 0.6, in fact, that's the same number, isn't it? I'm thinking my answer is going to be around 0.69 something, which is kind of weird. Does anyone have a calculator with them?
Yeah.
Do me a favor. Do the natural log of 2.
Okay. 0.6931.
Huh, that's interesting. Well, I got a really cool tidbit. I can't prove this for a couple more lectures. I want to do the infinite sum here. Well, we know the harmonic series diverges. We know that. We proved it. It's not a big deal. I just made the harmonic series alternate. This is exactly equal to the natural log of 2, which is really small, like 0.69 something or other. And you should be asking yourself, how the heck could this converge when the other one diverged? Well, it's a couple reasons. First of all, if every other term is negative, aren't they canceling each other out to some degree? And they're getting smaller. So they're kind of canceling each other out, but also not getting any bigger as a result. So we're going to find out some really cool things about alternating series. Basically, if I have a divergent series, but I make the terms alternate, there's a really high probability that that series will converge. Whoa. Now, today is all about how to prove that stuff. and had to come up with conclusions. But I just took an alternating series from something we already knew diverged. Now, what if I take a convergent series, like 1 over n squared, and I make those things alternate? Well, it's still going to converge, but to a much, much, much smaller value, because I just canceled literally half the terms, didn't I? So a convergent series, if I cancel all the terms, is going to converge to a smaller number. But what we want to look at is a divergent series. Is it possible to get convergence by making it alternate? And the answer is, yes, it is possible, but we need to look at exactly how that happens, okay? Any questions so far on this? Kind of crazy, kind of cool. Wow, okay? Now, if I do an alternating series in general, I don't know if it converges or diverges yet, so we're going to do the formal proof. But I wanted to show you by just examining two things that we already knew what was going on and looking at the harmonic, because that's the easiest one to play with. But this harmonic series clearly is going to converge to something. Again, very cool stuff. So, turn this off now. This is why I love using technology. It makes my life so much easier. Let's get smaller now. Okay, so here's the thing. I got to throw the what if at you. Now, we know this is true. We don't have to use this to prove anything anymore. If I took a series that was originally divergent, I could prove it this way. We don't like the integral test in general for a couple reasons. One is I got to do an improper integral. Okay, that's not our favorite thing. But it also means there's a high probability I've got to do an integration by parts on an improper integral. Because the only reason you're using the integral test is probably you have a logarithm or something icky, right? And I got to integrate that thing, and it's not really friendly. And so I want to stay away from it if I don't have to use it. So now let's consider the following. We're going to start with that alternating series right there, but here's the two conditions I need. I need the limit as n goes to infinity of an to be 0. Remember, if the terms aren't approaching 0, we already know it's going to diverge. That doesn't have to be proved. That's the nth term test. That was the very, very, very first test we learned, isn't it? So the terms have to be going to 0. And the second thing is that an plus 1 has always got to be less than or equal to an. We're assuming the a's are non-negative. Okay, we're assuming they're non-negative. So in other words, I'm going positive, negative, positive, negative, positive, negative. That's the assumption, that I am actually alternating on every term. So the A1, 2, 3, 4, those are all positive. I just happen to be subtracting every other term. Well, wait a minute, aren't these the two conditions? Aren't these the two conditions for the nth term test? So I'm assuming these two conditions are true. This should be kind of obvious, because if either one of these failed, then we already diverged. There's nothing to test. So these two have to hold. Turns out, this is all I need. I only need these two conditions to be true in order to show something. So let's look at our alternating series, this guy here. And what I want to do is look at the partial sums. So the first partial sum I want to consider, first of all, what would S2 be? Well, that'd be A1 minus A2. All right. What's S4? Well, that'd be A1 minus A2 plus A3 minus A4. Agreed? How about S2n? Well, that'd be A1 minus A2 plus A3 minus A4. I'll put a couple more in here. Plus, how about A5 minus A6 all the way to A2n minus 1 minus A2n. It's the sum of the first two n terms. Now, do you notice something about this quantity? If that's true, then doesn't that mean that an minus an plus 1 is always greater than or equal to 0? If every term's getting smaller or no worse than staying the same, doesn't that mean if I take the difference in this order, A1 minus A2, A2 minus A3, A3 minus A4, won't that always be non-negative? It can never be a negative number. It can only be a positive number or 0. So what does that mean? I want to take exactly an even number of terms. Well, look at this. This has to be positive, or at least 0. Non-negative, non-negative. Oh, so if I do that all the way down the line, can I safely say that the sum of the first 2 n terms will always be greater than or equal to 0? Now, by the way, the only way it could be equal to 0 is if every number was exactly the same. And that'd be kind of boring, right? In other words, I'd have to be using the same number over and over and over again to get 0. So in other words, it's never going to be equal to 0. It's always going to be greater than 0. Because if it was equal to 0, then again, I'm just doing the same number and I'm not approaching 0. All right, well, that was kind of interesting. But now let's do it from a different way. I want to group these slightly differently. Let me come over. Same S2n. I don't need this anymore. Now look what I did. I changed the grouping. So if I looked at this, it'd be the same as me saying A1 minus A2 minus A3 minus A4. Because if I distribute the negative, right, that gives me back my plus sign. Anybody catch that? So the odd indices are the positives. The even indices will be the negatives. So minus, negative, okay. So why is that important? Well, isn't that quantity greater than or equal to 0? And so is that one. And so is that one. So I've got, by the way, so is that one. And I'm subtracting every one of these terms. What does that mean? That this entire sum is going to be smaller than what? Than the first term. Does that make sense? I'm taking the first term and then I'm consistently subtracting positive quantities. Wow, that means this entire sum is less than or equal to A1. That puts now a really, really important boundary. Because didn't we just say it's always non-negative? And now we're saying smaller than the first term. So now we can say with absolute certainty. And by the way, these really are strict inequalities. They can't be or equals unless every term was exactly the same, and that's never going to happen. Okay? So in every case, we've just bounded this. Now, let's go back to the alternating harmonic series. We just did this on the computer and saw that it was around 0.69 something. And I said, you know, wink, wink, it's actually log 2, but we don't know that yet. We'll know that in another week or so. But we saw the number was around 0.69. What's the first term of the alternating harmonic series? Isn't the first term a 1? And then it was minus a half, plus a third, minus a fourth. The first term was 1, but the infinite sum added up to something that was smaller than 1. That's what that says right there. It was positive, but smaller than 1. 1 being my first term. Well, that's kind of crazy. So that means if I have an alternating series, all I need to happen is for it to pass the nth term test. That's it. That's all I need to happen for it to converge. Whoa. Okay, so there's 3 different cases we're going to look at here. Okay? And by the way, the fact that I'm starting at 1 is not important. And the second thing is, I'm doing n minus 1, but you could do any exponent. You could do the nth power. The only thing is if you start with the nth power, that just means your first term's negative and then you're going positive, negative. That doesn't change convergence or divergence. It just changes the sign of your final answer. So I like using that one because it's easier mentally to start positive, minus positive, and so on. Okay, I have 3 different possibilities here. First case is that this is the alternating series, this is the non-alternating series. This is the one we always start with. This converges. Second case is this diverges. Okay. I said there's three cases, but it's because the second one breaks into two possibilities. Now, I have a series that alternates, but my original series that didn't alternate already converges. For example, I've got negative 1 to the n minus 1 over n squared, n equals 1 to infinity. Well, we already know this is a convergent p-series, don't we? So now that it's alternating, it just means it's going to be a much, much smaller total. How much smaller? Well, it turns out, strangely enough, this one here, let's see if I got this right, I believe, by the way, does anyone remember the number we came up with on our screen?
For the ln of 2?
No, for the, remember when we did this one, had the first million terms or so? Wasn't it 1.64 something or other?
Mm-hmm.
You guys remember that?
I don't remember.
Well, I've erased it. When we did it the first 100, then we did the first 1,000, then we did the first million, we saw 1.64 something, something, something. Turns out, it's really cool. This is exactly pi squared over 6. It's exactly that. Do that on your calculator. Do pi squared over 6. It's just kind of a cool thing. It's not important in the long run. It's just a kind of a cool thing. What's pi squared over 6 roughly?
1.64.
1.64 something. Yeah, that's the 1.64 that we saw on the screen. So if I do an alternating series, what do you think? Well, isn't the first term of this positive 1? That means if I alternate, this total will be less than positive 1. The infinite sum here was around 1.64 something. But the alternating sum we now know is going to be smaller than the first term. It's going to be less than 1. It's going to be really small. So I don't need to do anything here. I already know this guy's going to converge because this guy converged. So here's what we do. If this converges, then our conclusion is the alternating series, and the language. If this converges, then the alternating series converges absolutely. Now, that's a word that we sometimes use in the English language, not in the right way. You know, I say, do you want to go to lunch today? Oh, absolutely. That's not what we're referring to here. What do you think the absolutely refers to?
At all points?
Absolute value?
Absolute value. See, I have an alternating series. Exactly 50% of my terms are negative. What if I look at the non-alternating series, where 100% of my terms are positive? That means I'm literally taking the absolute value of every term of the alternating series. So it seems like a strange use, but it's very, very important because it's the easiest case of all. If the non-alternating series converges, then the alternating series is going to converge absolutely because it's the same as saying I'm taking the absolute value of every term, so that it's no longer alternating. That's our favorite one because that's the easiest one. I don't have to do any work whatsoever. I say, well, the non-alternating is already convergent. We're done. There's nothing to do, no test to perform. Next case, this guy diverges. Ooh. Now there's two possibilities. The alternating series may converge, or it may still diverge. Okay? So now, this guy diverges, but the limit as n goes to infinity of an is 0, and an plus 1 is greater than or equal to an for all n at some point. No, this is pretty much for all n, period. This has got to start from the very first term. Every term has to be getting smaller as we go. That means I just passed the nth term test. So if this happens, like with the alternating harmonic series, what's happening is you have this effect going on. Right? They're alternating, but they're getting smaller in size, and therefore literally canceling each other out. That's why the entire sum is now smaller than the original first term. So if this is the case, then we say, And we use a different word. We say it converges conditionally. And that's huge. Okay? A condition means if the condition is not met, it will not converge. It had to meet this in order to converge. So it's called conditional convergence. Give you a simple example. And has anyone here applied for transfer? Did anyone here apply for a 4-year school out of high school originally? You know, you decide to come here later. My kids all did that. So you get accepted, right? I taught at a private high school years ago, and this would happen every single year. All these kids would be getting accepted, you know, sometime in the early second semester of your senior year, and then many of them just shut it down. I got accepted. And then at this particular private school, at least 50% of every single senior, every single year, lost their acceptance to the school they had been accepted to originally. At least 50% every single year. Because all acceptances are conditional. There's no such thing as an absolute acceptance. They're all conditional. And what is the condition, you think? That whatever got you in, you kind of maintained that behavior. You know, you did good in school, you continued, or you should say, doing well in school. So when you go to transfer somewhere else, let's say you just got into UCSD or San Diego State or someplace, and you say, wait, I can shut it down, and you fail all your classes this semester. Guess what? You're not going there. Yeah, all acceptances are conditional. If you meet the condition, then the conclusion will hold. Now, is it possible there's an absolute acceptance? Is that possible?
If you've already met the conditions required?
Well, yes and no, but what if you're in school right now and you say, well, I kind of messed up. Okay, so what you don't know is Chase here, he was just at the NFL Combine a couple weeks ago. So he did what the bench press, you know, you did it like 40 times, and he had a 52-inch vertical leap, and he ran the 40 in 4.2, which would be like Usain Bolt fast, and he scored a perfect score on the Wonderlic test and all this. In other words, he's greatest potential NFL quarterback you've ever seen. And he's going to a really non-academic school. Do you think it matters what grades he has? Or will his acceptance be absolute? Yeah, athletic scholarships are generally absolute. Why? Because you aren't going there to go to school. You're going there to play a sport. I hate to say it, but that's the simple reality. If you're a phenomenal athlete, okay, there's another situation. I worked at a private school, and there were kids that had a lot of money, and there were certain schools, I won't mention them, that parents were alumni of and parents were very wealthy. We had more than one kid not even graduate from high school, but had no difficulty whatsoever getting into this 4-year, very expensive school. Combination of the parents being alumni and could pay the entire 4-year bill in one shot easily, their acceptance was guaranteed. They didn't have to even pass their classes. But were they going to graduate from the school? Probably not. But 4 years of college paid up front, who cares? So conditional means you met these conditions. You have converged. If this guy converges, it doesn't matter. By the way, all convergent series had to have already passed the nth term test. Remember, if you fail the nth term test, your series diverged, period. It doesn't matter whether it's alternating or not. Failing the nth term test, your series diverges, period. So if you have a convergent series, it's already passed the nth term test. You didn't even bother because you went ahead and tried your limit comparison or your ratio test or your root test. You proved that series converged. So I have a convergent series. Making it alternate isn't going to change the convergence. It just means it's going to converge actually a lot faster because I'm wiping out half the terms. I have a series that diverged, but now I make it alternate. As long as my terms are getting smaller and approaching 0, again, like the alternating harmonic, they're wiping each other out. And I'm going to converge, and I'm going to converge to a number that is smaller than the first term. That's what we just proved. That's an incredibly powerful statement. But there's one more possibility. This guy diverged, and it did not pass the nth term test. Well, doesn't that already mean the alternating is going to diverge? Alternating isn't going to make you converge if your terms are getting bigger. Think of a geometric series with a big negative r. Aren't those like the worst things? They go like this. my terms are not approaching zero, my terms are not getting smaller, that series is going to diverge without limit. Oh, but wait a minute. Wouldn't the geometric series with a negative r be an alternating series? Because every other term is going to be negative and every other term is going to be positive. So that's the perfect example. I can still diverge because my terms are getting bigger. In fact, they're ballooning out of control and bouncing in both directions. That's the worst type of divergence. That's the diverge without limit. Okay? That is also a possibility. It's not the most common one. So what we want to do is start with the series and say, how do I attack it? So there is no test, by the way. There exists no tests on an alternating series, period. The number one terrible answer I get every single semester in 151 is someone will say, converges or diverges by the alternating series test. I've edited and reviewed over 25 textbooks and calculus books. I've never even seen that term in one. There is no such term as an alternating series test, yet that's the number one reason I get from calculus students as to why something's true or false. And I don't even know what it means. Like I said, I've helped co-author some of these books. There's no such test. No, you can't test an alternating series. There's nothing to test. You test the non-alternating series, and then your conclusion is about the alternating series. So let's do several simple examples. Because now the nature of things pretty much from here on out is everything's going to be alternating from here on out. Because next day we're going to throw variables in. And variables can be positive or negative. Okay? So let's start something simple. Let's say I'm going from 3 to infinity, and I've got -1 to the, I'm going to go ahead and go nth power this time, and I have 2n squared minus 4n plus 3. Okay. Whether that's n or n plus or n minus 1 makes no difference of convergence or divergence. It only makes a difference of what it converges to. If I go positive, negative, and I converge, I'm going to converge to a positive number. But if I go negative, positive, and I converge, I'm going to converge to a negative number. And it's going to be the opposite sign. It's no big deal. So that doesn't affect it. I look at this and I see an alternating series. So here's what we're going to do. I want to write it out. We are going to test, or I like using the word consider. That's what I often say. Consider this series. Let's determine what happens to this series. Now, if this series converges, then my original series is going to converge absolutely. If this series diverges, now I will run the nth term test and see if that passes. If it does, then this will converge conditionally. If this series diverges and it fails the nth term test, then my original problem diverges. Those are the 3 cases. Okay? So, what do you want to do? What kind of test?
You could do a direct comparison test.
It would be harder. It might be easier to do a limit comparison. Yeah. You could, the negative on the bottom kind of messes things up because but the coefficient helps things. I can probably do a direct comparison, but then I got to figure out how many terms I got to go out, and I'm too lazy. Let's just do limit comparison, okay? Yes, you could do a direct comparison, but it probably involves more algebra, actually. So, we are going to do what? We are going to compare
To 1 over n squared.
to the sum of 1 over n squared. And by the way, I'm going to say n equal 3 to infinity because I kind of want them to start at the same place. Starting later, we already know cannot affect convergence or divergence. Right? It cannot affect convergence or divergence. It just means I don't have the first 2. Big deal. All right. So now, we take the limit as n goes to infinity of this divided by 1 over n squared, so times n squared over 1. And that would be n squared over n squared minus 4n plus 3. Can I do this limit without doing any more work?
Oh, you're forgetting the 2.
Yeah, the degree of the numerator and denominator are the same, so I can just take the ratio of the lead coefficients.
You're forgetting the 2 by the n squared on the
Oh, thank you, Cece. That's a 2. Good. That is important. So what is this limit?
1/2.
If I, by the way, could I have done it in reverse? Could I have done 1 over n squared divided by this quotient? Could I have done it in reverse? Yeah, and then I would have gotten a limit of 2. And this is less than 1. And this is greater than 0. If you say either one of those statements, then no matter what you say afterwards has nothing to do with anything, and a right answer now is an absolute yes. You're not comparing this to any number, positive or negative. You're saying it is finite and not 0. It could be positive, it could be negative, it could be really large, it could be really small. If you're comparing the limit comparison to another number, anything you say after that is worthless. Because it's an absolute incorrect validation of whatever conclusion you get. No, limit comparison, I'm looking for finite, but not 0. 0 would mean I compared it to the wrong thing. Infinite would mean I compared it to the wrong thing. It's finite. So in simple terms, it means that this series is acting about 1/2 as big as this series. That's what that means. But this guy, we left one thing out. It's kind of important.
Which was all.
A conversion series.
I did that on purpose because we're ready to make a conclusion. Converge or diverge? I don't know. Because what did I compare it to? When you make your comparison right here, you've already indicated what the final answer is, haven't you?
Yeah.
I'm comparing it to a convergence series. I know I'm going to get convergence as long as I don't mess up the algebra. So a convergent p-series. So therefore, there's 2 things now. We just tested the non-alternating series. I didn't do a limit comparison test on the alternating series. That's not possible. It's impossible to do a limit comparison test with that -1 to the n because it doesn't have a limit. I can't take the limit as n goes to infinity. That would be a DNE. I want to make that really clear. If you try to take a limit of something like that, right, that's just bouncing back and forth. So what we just concluded is let me write it all down. This converges by what test?
Comparison test.
By the limit comparison test. Therefore, I know it's a lot of writing, but we don't want anybody to wonder what our conclusion actually is. Now I can tell you what's happening to this guy. Anybody want to try? It's either going to converge absolutely, converge conditionally, or it's going to diverge.
Converges absolutely.
Converges absolutely. Beautiful. There's nothing about this that should be difficult because you say, well, we've already done this. This is what we did for the last 2 weeks before the break, right? We practiced proving things converge or diverge. Now we're going one step further and saying, well, what if I alternate? Might that affect things? But it'll affect things only in a good way. I'm going to get a lot more things converging than I was before. But the fact that the non-alternating already converge means whatever this, if I use the computer to figure out what this does, whatever this does, this is going to converge to something much smaller. That's it. That's what we can say. All right, let's try another one. We've got as I start at 2 because it's a natural log. Oof. Sorry. And let's do, I'll go 1. Doesn't matter. All right. Again, it doesn't matter as long as it's alternating, whether it's n or n minus 1. Okay. So, we start the problem. So let's consider this one. What do you think? I don't want to do an integral test. Oh, God. Oof. There is an easy one. Is it true? Is the following statement true or false? I'm going to put 2 because that's where we're starting. Is this true or false, this statement there?
True.
Log n is always smaller than n. If I drew the graphs, sometimes it helps to think, right, there's the log graph, there's the, it's always true. Okay, why is that important? Because then 1 over log n and 1 over n goes the other way. Or I'm sorry, goes the other way, I say. Is that a good thing? Yeah. What kind of test are we going to perform? Direct comparison on the harmonic. You see, this is going to be an easy one. We're going to do a direct comparison on the harmonic series. Because 1 over the log will be bigger than 1 over n. Okay, so this is true for all n greater than or equal to 2. So then I can say this is true. I have to show term by term, and then I can say the sum. Now we use an example. If I paired everybody in this row up with everybody in this row, and everybody in this row was taller than the person next to them, then the total height of this row has to be greater than the total height of this row, because one at a time they were greater. Right? That's all we're saying here. So what can you say? So this. Oh, we never actually wrote what we're comparing to. Sorry.
Shouldn't the n equal 1 be an n equal 2?
Did I write? Oh, thank you. Yes, thank you, Jason. I got it everywhere else, didn't I? We need to compare to what? To this. That's 2. A divergent or harmonic. Both would be correct. Okay? I really need to say that because the divergent part is huge. Okay? I compared this series to a known divergent series, and it was term by term bigger, therefore its sum was bigger. Therefore, I can say this, converge or diverge?
Diverge?
Diverges by, what test did we do? By the direct comparison test. Great. So I'm all done with the problem now, right? I can now say this diverges. No. Now the work begins.
Oh, that's just for all n greater or equal to 3, right? Instead of 2? The ln?
Well, no, aren't we starting at 2?
But like that only true when the ln like 3, when the n greater than 3?
Well, log 2 is smaller than 2.
Yeah, but the 1 over ln of n, is this like for all n greater than 3? Because 1 over n of 2 is like 1.4.
Well, what's log 2? How big is log 2?
I think of the second one.
Right, no, but how big is log 2 is smaller than 2, correct? So 1 over log 2 should be bigger than 1 over 2. So this should start right at the beginning. Now, if it didn't, yes, we could go down the road. Are you hitting the right button?
I think he's saying that 1/2 is smaller than. Yeah.
1 divided by log 2 is 1.44 something.
Oh.
Yeah, no, this is true from the beginning. It's not, is it always true from the beginning, or might I have to go 1 or 2 terms down the road? By the way, if you said 3 or 5 or 20 or 1,000, would it change your conclusion? No, because at some point it's true from that point on. That's the key thing. At some point it's true forevermore. It just so happens that in this case it's true from the very first step. And that's because we recognize here that the log was always smaller than the n. So therefore the reciprocals were going to flip. We had to start at 2 because log 1 was 0. Okay? So now we've just shown, and this was a fairly easy thing to do because this is what we've already done. We proved that this guy diverges. So now let's go back to the original problem. Is it possible that the alternating series still converges? Yes. Even though we rarely perform this test, now we're going to do it. Is it true that the limit as n goes to infinity of 1 over log n, is this a true statement? Is that true? As n approaches infinity, log n is going to grow without bound, therefore the reciprocal is going to approach 0? Yeah, so that limit is 0. And secondly, log n plus 1 is always bigger than log n, therefore the reciprocal is always smaller, isn't it?
Yeah.
And this would be true always. This isn't true down the road, this is always true. So I'm going to put it check, check. So now what can I say about the original problem?
Converges conditional.
Converges condition.
And by the way, Wolfram will actually do an infinite sum. Oop, hold on. Come on, come back. I'm just going to do it. I'm not going to bother. Well, actually, I don't know if you can see it. I saw someone, I visited a class last week and someone was doing this and they were projecting onto the board, that way they could write on the board while they were doing it, which I thought was a great idea. It was just really, really hard to read. Okay, I don't think you, I'm going to show you something here. We're going to do this problem right here. Okay, what was it? It was -1 to the n minus 1, okay, over, here we go, ln n, okay, from 2 to infinity. Let's see. Hold your. Okay, can you see? I don't want to bring the screen down. It just takes too long. Can everyone see that?
Yes.
How can you read that number to me?
Negative 1.01 862.
We just did this. We just did this infinite sum of a known divergence series, but when we made it alternate, it converged to right around -1. Isn't that crazy? That's the whole point of this. We proved that 1 over log n, that series, diverges. But now when we made it alternated, it not only converged, it converged to a very small number because, again, everything kind of wiped each other out. Because it starts like this. It's going boom, 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 boom. It's oscillating and getting smaller and smaller and smaller. That's all we needed to happen. We just had the terms get smaller and approach 0. Okay?
What do we do with the imaginary number?
With the imaginary number?
Yeah, because it has I in there.
Oh, don't worry about that. That's, yeah, one thing, if you know how to use Wolfram, you know that the technology, they love giving you complex and imaginary answers. Has anyone used Wolfram to do integration? I love using it. You ask it for an integral, it usually gives you 7 answers and 4 of them are complex. One of them will be the actual one you want. You just have to know how to filter through. Yeah, it always gives you extra stuff that you don't need. So we'll leave it like this. And by the way, do you notice what it also does?
It turns ln to log.
Yeah, by the way, every math course you will ever have after calculus, when you say natural log, it'll always do log, which is evil. Why? Because it's the only, outside of chemistry, it's the only log you're ever actually going to use in any situation for the rest of your life, in every field, except chemistry, because that is log base 10. So I'm not a big fan of that. I'm not a big fan of them changing it. You know, but that's what people do. They just automatically, when they use log, so what if they want log base 3 or log base 10 or then they actually write the subscript. They'll actually write the 10 in at that point. Again, not a big fan of changing symbolic notation because it's very confusing. But if you've used Wolfram or Desmos or any of these, you'll notice it always writes log when you write ln.
So when we reach the conclusion that a series converges conditionally, do we also then put by the nth term test?
No.
No?
No.
Okay.
You can't do anything to this. You proved this guy diverged, but you also proved that this one passed the nth term test. This one passed the nth term test.
Right.
An alternating series cannot pass an nth term test because they are changing sign. Remember, alternating series, the terms have to at some point be getting smaller forevermore. But if they're changing sign, they're not getting smaller forevermore.
No.
They're alternating forevermore. Oh, that's why I can only test the non-alternating. See, that's why you can't test an alternating series. It would always fail everything, no matter what, because the terms are alternating signs. So they're definitely not getting smaller. You can't go positive to negative and back to positive and say you're getting smaller, right? But the absolute value of the terms are getting smaller. That's the important thing. That's why when we do the non-alternating. Okay, these are important questions, but it's also not that hard to work with in some cases. It's kind of cool. All right, let me turn this back off again. Now, obviously, there's another case. This is a good one. Where you will be tricked sometimes. Could I write this as -2 to the n? Would that be legal to write it like that? But if I see -2 to the n, it's not as obvious, is it, that what's going on? I want the -1 to a power, so then I can choose to ignore it for the non-alternating. When you see the -2 to the n, which you may sometimes do, there's another one that you also might see. This is even more evil. Instead of this, oh, by the way, if I grab my TI-89, my titanium, of course, and I enter that, it'll immediately change it. Does anybody know what it'll change it to? It won't be that. It'll automatically change it to cosine of n pi. What? Well, what's the cosine of pi? Isn't that -1? What's the cosine of 2 pi? +1. 3 pi? -1? It's the same as -1 to the nth power, isn't it? For integer n, -1 to the nth power and the cosine of n pi are exactly the same for every integer value of n. So sometimes the technology will change it to this because it's easier for it to work with. So when you're doing a problem and you see this, everybody, I want you to interpret this is this. They are exactly the same thing. Because n can only be an integer in this case, right? It's an index. For real numbers, that's not true. If I raise -1 to a real number power, then I'm going to get imaginary numbers generally and back again. Or I should say complex numbers. It's even worse. So let's start this problem by considering the non-alternating. All right, now what test do you want to perform on this? Can you do limit or direct comparison or even integral test? If I was in a really bad mood, I'd make you do integral tests, and I'll come back next week because no one will actually get anywhere because, yeah. No, you're not going to do integral tests. But you can't do a limit or a direct comparison either because of the exponential. So what choices do you have here? Ratio or root. And they're both going to be about the same level of difficulty, but most people would probably go, which way do you think? Most people probably go ratio because the root test is a little trickier to rewrite. It's correct, but it's a little trickier to rewrite, and there's a weird limit in there somewhere. So I think we should probably go with the ratio test. So we want the limit as n goes to infinity. Now we're not comparing it to another series. We're going straight to the ratio test of 2 to the n plus 1, n plus 1 cubed divided by 2 to the n. So I can do this. And I said, in general, remember, now there are no negative terms here. So the absolute value in this case is redundant. It is not going to affect your answer. I just want you to get in the habit of writing absolute value. Because starting next day, every series you will do, starting next day for the rest of your life, will have variables. So leaving the absolute value out would give you a completely incorrect answer 100% of the time. So I want you to get used to the absolute value when it actually isn't necessary, because it will always be necessary after today. Again, the moment I throw a variable in there, not having the absolute value completely changes the answer. So does this reduce at all? Well, the 2's certainly cancel, right? So what do I have on top? 2n cubed, and on the bottom I'd have n plus 1 cubed. Does that look right? All the 2's except for one of them cancel. Do I need to do L'Hopital's rule? Yeah, I can do it 3 times. I can multiply top and bottom by 1 over n cubed and work it in, or I can just notice that the bottom is a cubic and the lead coefficient is still going to be a 1. So I don't have to do anything else. I can say the answer is 2. Sometimes we don't realize that we know that. That's Calc 1, we knew that. You don't have to do anything at this point because they're both 3rd degree, so it's got to be the quotient of the lead coefficients. Now, not 0, 1. That means that this original, or I should say this guy here, this is a series that thinks it's geometric in nature. Why? Because we just did the ratio of consecutive terms and we found that limit was constant. That means this series thinks literally it's 2 to the n. But wait a minute, that's divergent, isn't it? Isn't the sum of 2 to the n divergent? Because r is bigger than 1? We just did the ratio of consecutive terms and we got a limit that was bigger than 1. So what does that mean about my terms? The non-alternating terms are getting bigger or smaller?
Here.
Bigger. So this series does what? Diverges by the ratio test. You're going to like this. If you're diverging by the ratio test, what are you saying? My terms are getting bigger. Is there any reason to perform the nth term test? No, your terms are getting bigger. If you diverge by the ratio or root test, you can only diverge if your terms are getting bigger. So you never have to do the nth term test on the ratio or root test. So we're done. Tell me about this guy. It's going to diverge. Will this diverge to infinity?
Yes. Well, no.
No, it's going to be the evil without limit. Remember, I said the non-alternating thinks it's 2 to the n. In other words, it's asymptotic to 2 to the n. Oh, that means this guy's asymptotic to -2 raised to the n. And isn't that the worst type of geometric series? The big negative r? So if I wanted to know the actual behavior, yes, it diverges, but in the strictest sense, it diverges without limit because it's oscillating and getting bigger. So if I was doing a limit comparison, I would need to do the nth term test at this point. But because we did a ratio test, and we just proved that the terms are all getting bigger. Why? The ratio of consecutive terms is approaching 2. That means every term's getting bigger, and it also means that none of the terms are approaching 0. They're getting infinitely large, not small. So you don't have to do anything else. You like that, don't you? Besides which, does anybody want to take a limit of this as n goes to infinity? So let's just suppose you were going to be ornery and you wanted to do this. You wanted to do the nth term test, which, by the way, more power to you. You wanted to do this, and you also wanted to show that 2 to the n plus 1 over n plus 1 cubed is always smaller than 2 to the n over n cubed. You wanted to show, right? Or you wanted to determine. Algebraically, this would be a nightmare, just so you know. How do you compare the n and the n? Everybody realize that trying to do this would be really difficult. What do you got to do on this one?
Rewrite it.
Well, you could do e to the limit, or excuse me, e to the log, or you could do L'Hopital's rule 3 times, but you'd have an exponential function, which derivative is a little bit tricky. You could do this. I don't really want to do this, but yeah, there's no shortcut for this one. You'd have to do L'Hopital's 3 times. That means you're differentiating the top 3 times. It's all correct. And by the way, will you get 0 as a limit for this one? Does anybody know? Well, if I do L'Hopital's rule 3 times, my denominator will eventually be a constant, won't it? But my numerator will still be an exponential function, which means that limit will be infinite. Ooh. But I got to do a lot of work to show that. This one, algebraically, is going to be really difficult to manipulate. But like I said, you don't have to do either one of them. Again, ratio or root test, if it diverges, it's already failed the nth term test because it means your ratio of terms is greater than 1. They're getting bigger, and they're not approaching 0. Can't be approaching 0 if your ratio is bigger than 1, right? They're all getting bigger. So that is not the worst case. The worst one would be something that fails, let's say, a limit comparison, or I diverge by a limit comparison, but my terms are also not getting smaller, not approaching 0, and I actually had to do an nth term test. That's probably the least likely of any of them, okay? Let's try another one. Let's do, is there any problem with n equals 0?
No.
What would the very first term be?
1.
It'd be a 1 because numerator and denominator would both be 1s. Agreed? So that's not a problem. If I can't start at 0, then you start down the road. But starting at 0 is not only not a big deal, you're going to find that after today when we introduce variables, we're actually going to start at 0 most of the time, as it turns out. And there's a reason for that. But the starting point, we note, does not affect convergence or divergence in any way. What the starting point matters is, if it does converge, what does it converge to? Okay? So, I'd like you to start this one for me now. Okay? And use the same language we've used in each problem. Consider the non-alternating series as your first step. And while you're doing that, all right, what test are you going to perform? Do I have any choices on this one? How do you know that? What's the giveaway? The factorial. That's very important that we recognize. If it's a factorial ratio test, there's nothing else that can be done. But we don't mind. Now, that's not a hard ratio test in this case. In the previous example, I said it could be root or ratio because it was exponential. But factorial means it's got to be root, or excuse me, got to be ratio, which is why most people, they use ratio way more often than root tests because of the factorials. So now writing this correctly is key. Is this correct? No. Well, that would be as correct, by the way, as writing, that. And we all agree that that's a bad numerator, correct? I'm replacing n with n plus 1. I'm not adding 1 to any quantity. I'm adding 1 to the n. And that is a common mistake. We sometimes mess it up. So what should be here?
Plus 1 factorial.
N plus 1 quantity factorial. Yeah, not n plus the number 1 factorial. Now, divided by that, or times that reciprocal. Now, this is what I would do, just to make it easier on myself. I like doing that because when you're canceling, we all know that when we cancel, especially with exponents, and we cross things off, we sometimes lose a term because we just put a line through everything. And when you put a line through everything here and here, might I lose that 10? Yeah, that actually happens often. So I'd rather do this and say, okay, I'm canceling that guy and that guy, that have 10 left over. I'm canceling that guy and that guy, I have an n plus 1 left over. I can't possibly make an algebra mistake if I do it that way. Now, every term is positive, so I can drop the absolute value. And so what does that give me? The limit as n goes to infinity, what's left?
10.
10 over n plus 1.
10 over n plus 1. Huh. As n grows without bound, what is that approaching?
0.
So my limit is 0. Which is less than 1. That's important. What does that mean? That means these terms are getting really small, really fast, and they're alternating in size. So do you think the sum's going to be very big? Well, I mean, the first couple of terms, right? Let's just write out the first couple of terms. So what did I get? I had 0, you said it was 1, then minus 10 over 1 factorial, then plus 10 squared over 2 factorial,
Yep.
then minus 10 cubed over 3 factorial. These are still getting really big, aren't they? But at some point, the factorials are going to overtake the exponentials, aren't they? At what point? I don't know. Maybe 15, 12, I don't know. Somewhere in the teens, probably. Now, what do we know about this whole sum then? Since it's alternating and you just...
Converges absolutely.
So this guy, first of all, this guy converges by the ratio test. Let's make sure we say that. Therefore, this series converges, and in words, absolutely. Can you tell me something about what it's going to converge to?
A number less than 1.
A number less than 1. Which does seem odd, doesn't it? Because these numbers are getting really big. So what does it converge to? You're going to like this one. Is this coming on?
There it goes.
There we go. Can you, oh, hold on a second. You can't see anything. This one's actually really cool. Like that. Let me make this bigger. It converges exactly to 1 over e to the 10th power. Well, that's kind of crazy, isn't it? That's really small, by the way. Is it less than 1? Yeah, it's less than 1. Wow. Now, in a couple of weeks, when we start adding, ammunition to our arsenal of how to do things, you will actually be able to tell me that answer. You will actually be able to come up with this on your own. We won't require anything clever. It's about recognizing the behavior. There are certain series that are really common, series particularly that involve e, sine, and cosine. We're going to see down the road. Series that involve these, not in the summations, but in the result. We're going to be looking at things that produce e's and sines and cosines. That's very cool stuff, very, very powerful stuff. Okay? So that's interesting, right? Wow, those first few terms were getting really, really big, but because of the canceling effect as they had, this adds up to a very, very small positive number. Any questions so far? Yeah, let's keep going. So, are we doing anything different along the way? No. We're doing exactly what we've done previously. We just have literally an additional step to take place to determine what's happening with the alternating thing. So we got that this guy converged by the ratio test. Therefore, in words, you'd say this converges absolutely. This does not converge by the ratio test. You can't do any test on an alternating series. Because if you did, it would always fail the nth term test. Alternating series can't pass an nth term test. The non-alternating passes. And that's how we started the class, by saying, what if we consider the terms, all positive terms, and then say, what are they doing? Then we proved using the nth term test how we can get conditional. But again, you can't test that guy. You can test that guy. All right, let's do it. Another ugly one. Let's do even thing of Oh. That does look kind of scary, doesn't it? But
Mm.
So that's -1 to the n times that whole thing to the n?
yes.
Okay.
I guess technically we could put a negative sign in front of the quotient and then do the n, and it would not be different, but it might be harder to recognize. Does everybody agree? If I simply put the negative sign in front of it, it might be harder to recognize that we have, you know, a -1 times this thing all being raised to the nth power. So I'd rather write it like this. So now we will consider the fact that I'm starting at 1 is not significant, okay? You want to do a limit comparison? Because it kind of looks like a p-series, except for the
And so it's gotta be a ratio test?
root
Root test.
test. Because right now it's in the form an raised to the nth power. So the root test is the only test we can do here. But it's recognizing that. So we looked at this, I think the last day we were all meeting before the break, right? So if I do the root test, I'm not testing the exponent, I'm testing the base. So now we're looking at the limit. I guess in the strictest sense, you could say I'm looking at the limit of all of this stuff and then to the 1 over nth power, which to me is kind of silly. Just how about all of the stuff without the exponent? That's why it's called the nth root test, because technically I'm taking the nth root of this. Now, what do we get?
2/3.
2/3.
Yeah.
And that's finite, not zero?
Yes. Well,
That's
this
true.
isn't- This isn't the integral test.
But that's not what I'm looking for. What am I looking for? What number am I comparing this to?
0.
Ratio and root test, I'm doing the exact same thing. I'm comparing it to the number 1, and it is smaller than 1. Remember, the ratio and the root test both you're using because your original series is acting like it's a geometric series. And what you just said was, this is acting like a geometric series with an R of 2/3. So think of it this way. I'm saying I believe the behavior of this thing, it's behaving like this guy. That's what you're saying when you're using the root test. And as long as the absolute value of R is smaller than 1, I'm good. Everybody okay with that? So this means what? This statement right here means what?
Converges.
That this guy converges by the root test. Okay? So about this guy.
Converges absolutely.
Converges absolutely. I didn't need it to alternate in order to converge. It would have converged anyway. So now all that means is it's going to converge to a much smaller value. In fact, what's the very first term of this series?